Hello, hello. It's good to see you for lecture six. Lecture six. I'm so happy to see we have so much to talk about again. Physics is so amazing. There's so much good stuff to talk about. We're not going to be able to talk about it all, alas, but we'll talk about the cool parts, at least today, of particular aspect of stuff building on yesterday's activity. I mean, I shouldn't say yesterday because you might have watched the previous lecture before yesterday. Nevertheless, might have watched it this morning. Who knows? Hey, but anyway, remember the whole pressure equals force over area stuff we talked about the last lecture, right? And how you could take advantage of the different pressures and the different, like the third law of motion with the rocket and so forth, and the air pressure, the Wright brothers, the Bernoulli, the airplanes, and how different pressure of air can cause the different results of where you're moving and how you're moving and things like that. Now, I want to extend that idea a little bit further. I'm going to go back to orbital velocity. We were talking about like if you were able to move in such a way that you kept going, right? You kept going and they went around the Earth, and then whatever what you had before would wind up hitting you on the other side. The orbit, the concept of a thing moving all around, right? What does that mean? What it actually means, and this is going to lead to the whole thing that we want to talk about today, right? If a thing is moving around the Earth like that, right, it's experiencing force, is it not? Right, it's experiencing the force of two different things. It's experiencing the force of being pulled toward the center of the Earth, right? But it's also experiencing the force of being pulled outward by the motion. Remember, if I take a thing and I start spinning it around my head, and I let it go, right, it goes flying. What will happen is that it will go off in a straight line. It won't actually fall, like spiral around me. Let's go off in a straight line. So there's actually two different forces that are involved. One force is pulling them toward the center of the Earth, if I'm in orbit around the Earth. The other is pulling me outward, right, as a result of my moving around in a circle around the Earth. So what happens is, although I'm experiencing two forces, what happens is that the forces cancel, right? So I wind up not having any net force on me as I'm moving around. Now, this concept of the net force is really important, right? Because if you have a certain amount of pull, a certain amount of push, and it turns out to be exactly the same, then you're not experiencing any force at that moment, right? Well, you're experiencing force, but you're not experiencing net force. The total amount of force added up around you turned out to be zero, right? So it's as if you were experiencing no force, even if you're being pulled and pushed at the same time. So what does that mean? Well, when you're orbiting, you're weightless, right? Weight is a gravitational pull that you're feeling on you. So like if I weigh 100 pounds, it's actually that I weigh 100 pounds here on Earth because the gravitational force on me at the surface of the Earth is 100 pounds. My mass, right, the F equals ma part of the mass, is probably like 45 kilograms, right? And that doesn't change no matter where I go, but my weight will change. So if I go on the surface of the moon, for example, my weight, instead of being 100 pounds, will be closer to 16 pounds. And that's just because the way that the force of gravity works, the amount of acceleration from gravity at the surface of the moon is different from the acceleration at gravity at the surface of the Earth. The Earth is bigger, the Earth has more mass, the Earth is larger. All of those things build into that. So if you're weightless, what's happening is you're falling, right? You're always falling. You're not experiencing any push or pull net. You're just kind of being there, right? So if you're in a fall, if you're free falling, when this thing here right now, right, it weighs a certain number of kilograms, or right now when I'm sitting, I weigh a certain number of pounds, right? But I have a mass of a certain number of kilograms. That's the right way to say it. But if I'm falling, whether I'm falling in a way that I miss the Earth and thus go into orbit, or whether I'm falling, free fall, right, toward the ground, I experience at that moment no weight. The net forces on me, nothing's pushing against me. That makes me feel like I have weight. I have mass at that time, but not weight. So that's weightlessness, right? So that's kind of interesting. But wait, if I'm not feeling any weight, if I'm weightless, does that mean I have no longer anything? Like, do I have any other quantities in myself the characteristics of my motion, does it matter? If I'm not weightless, does I have nothing? Well, turns out I have something else. As long as I'm moving, I still have this other thing that doesn't have to do with how much force is on top. Okay, and herein lies a really cool thing. I got to give you this sort of mental picture between something that we've been talking about up to this point, like force, okay, and this other thing which I'm going to talk about later, which also shares this particular characteristic with mass. And you've seen this in some of your previous homeworks before. Let me just re-emphasize this point, okay? Force is a vector quantity, okay, a vector quantity. Vectors have both magnitude and direction, right? So for example, if I'm feeling a force, it's a certain number of newtons downward or upward or off to the side or left to the right or at a 45-degree angle or something like that, right? So it's a vector quantity. Force, momentum, those things are vector quantities. But something like mass, like my mass is 45 kilograms, right? That is a scalar. That means it scales. It does not have to do with direction. It only is an amount. Okay, so no matter what direction I'm moving, my mass stays the same. That makes sense? There's no change. Like I could be moving 15 meters per second up this way. My mass is 45 kilograms. If I'm going this way at 15 meters per second, my mass is 45 kilograms. In other words, the direction of my mass is not important, right? Similarly, I might say vector quantity if it were velocity, right? And the scalar quantity would be speed. I know those words feel like the same thing in our regular lives, but when we're talking physics, it's actually a little bit different, okay? So a vector example would be velocity, 13 meters per second down or something like that, right? You can remember that by remembering that v vector and v velocity start with the same letter. Now a scalar would be example speed. How fast are you going? 13 meters per second. Okay, that's a speed. I didn't ask you what direction you're going, so that's a scalar. Okay, so vector quantities and scalar quantities both coexist in physics, in life, in everything, and it's something important to remember. So now we have force. If your force is 0 and you're moving, like in an orbit around the Earth, for example, or if you're free falling from an airplane before you pull your parachute open, you may be experiencing a net force of 0, but you still have a scalar quantity that is inherent to what you are doing at that moment, okay? And it depends on your speed, all right? And that quantity, that kind of thing is called energy. Energy, right? Energy, there's actually a song about that energy stuff. This dates back to Schoolhouse Rock days. Take a look sometime if you want to find. I bet you'll find it on YouTube. It's actually kind of a funny song because energy is an odd word for us in our society. We think of energy as both this thing that I'm about to describe, right? The amount of energy an object has as it's moving, or the amount of energy that is stored in a gallon of gasoline and stuff like that, and the actual energy sources themselves. So sometimes when we talk about energy crisis or something like that, we're actually meaning that like we're running low on natural gas, or that we have a shortage for market reasons of gasoline or heating oil, or something like that, or wind and solar and nuclear and things like that. So our society mixes up the word what energy means, right? So in physics class, what we're talking about now, energy is specifically that thing, right? It's hard to describe even with regular words, but it's that thing that is that causes stuff to happen in the universe, I guess, the world, in our human bodies, right? If something has energy, then it can do something. Make sense? Right. And it's a complicated concept because as we talk about energy, you'll see there's lots of different forms of energy. And energy can be stored, and energy can be transformed, and it can show up in different ways, and it can change and things like that. So the concept of energy is really very hard to get a hold of. Okay. So in fact, after Isaac Newton figured out force and what that was, like in the 1700s, it wasn't until the 1800s that people figured out what energy actually is. All right, so I'm going to write out the word energy because that's kind of cool. So remember, and remember what this energy is. This is specific to objects, right? I'm not talking about like mental energy. We're not talking about those kinds of other kinds of energy, but this kind of energy, this physics aspect of energy, okay, was primarily, today we give credit to a guy named James Joule, Joule, who figured out that falling water could turn a paddle wheel, right, which people knew for a long time. But the actual thing that was happening was that the water had energy, which was being transferred onto the paddle wheel and causing the paddle wheel to spin. So the energy was being transferred and was causing work to happen. Does that make sense? So this word work, work, work. Okay, energy and work in physics can sometimes be interchangeable, but work is like what happens when you put energy into a system and it does something cool. Okay. Now later on we can talk more about how energy and work are related and how there's energy that doesn't do work. And that's kind of a cool thing to think about too. But we'll have that conversation probably in the next lecture. What I want you to gather right now is that this guy, James Joule, basically figured out that there is a relationship between the energy that something has and the amount of work that can be achieved as a result of that energy. Okay, that's actually kind of cool. And how do we measure energy precisely, right? Well, let's think about this. I got this water bottle. Now I've been drinking it for a while now. Over a period of several days. I keep refilling it, it's whatever. So right now it's not all the way full, but when a water bottle is all the way full, right, it has a mass of about half a kilogram, 500 grams, right, a little bit more than a pound. So this is a mass of 5 kilograms. So let's say this thing is dropping, right, and right now it's about a fifth of the way full. So I would say that this has a tenth of a kilogram's worth of water. The total mass of this thing is like 0.1 kilogram, thereabouts. Okay. If I drop this thing a full meter, 3 feet and change, if I drop it this far, okay, and I'm going to try to catch it in a moment down over in this hand. If I drop it this far, as it's falling, there's no weight on it, right? Because it's in free fall. It has a mass, 100 grams, but it feels no weight at that moment. Once it hits my hand, there is a force, right? Because my hand is pushing back up against it. The pull, the force that's caused by gravity, right, winds up pulling on it and boom, right? Then I have a force. And then this is equal and opposite, right? There's a force coming down on my hand as my hand is pushing up on it, and it creates a balance. While it's falling though, right, how much energy does it have? Now that is kind of cool. Because what happens is that as it falls that distance, it gains energy as it falls because it's speeding up. And when you're moving at a certain speed, then you get a certain amount of energy. Okay, that energy manifests itself in the motion. So as I drop this, if I had 1/10 of a kilogram here and I drop it about 1 meter, all right, by the time it reaches my hand, 1 joule of energy will have been released. Okay, so this thing had 1 joule of energy that turned from it sitting still up here, me holding it up here, and causing its motion down through in this full meter's worth of distance. Not cool? All right. It's okay if you don't get it right away, but think about how that goes. Let me reverse the conversation. Let me take this, okay, sitting on my hand, right, about 1/10 of a kilogram, and let me move it up. Let me take this and move it up a meter. So, 3 feet, 4 inches thereabouts. That took effort, didn't it? I did work. Make sense? I had to work to get this thing up to here because it has a force, right? Force of gravity, which would work on it and has been working on it because like it wasn't in free fall, remember, it's in my hand, right? So now it's in this hand, right? It's in this hand. I'm going to move it up an entire meter. I had to work to get it up there. And what happened was, remember when I dropped it, it has a certain amount of energy, right? I have imparted into this object an equal amount of energy, but I put it up here. So that's work. I know I'm going around in circles, but does that make sense? Energy, work, energy. The connection is actually very, very important because every single machine, every single biological system, chemical system, physical system, astronomical system, every system in the universe has this exchange between work and energy. If you have a certain amount of energy, you can do a certain amount of work. Sometimes you do less work than you have total available energy. These are all the different ways that things happen all around us. Okay. So once again, I'm doing work if I take like this object, move against the force in the opposite direction, right? A certain distance. And when I multiply that force by that distance, then I wind up with a scalar quantity. I wind up not with a vector again, because the distance is kind of, when I multiply them, they kind of go away, right? It's coming down, the force, the distance is going up, I multiply them, that's the amount of work that I did. And then when I have up here, right, this has energy in it, even though it's not moving. It's the energy that I put into it by moving it up here, right? But it's like not something that you burn. It's not gasoline. It's not natural gas. It's not coal. It's got this energy sitting there. It potentially could fall at any time, right? If I let it go, then it will fall. But it's a potential. It hasn't been revealed. It hasn't actually shown up in motion yet. So this potential energy, by me moving it all the way up here, I've given it potential energy equal to the force times the distance. And then when I let it go, and that energy that I put into it, and it comes back to the original height where I lifted it from, that energy is the energy of motion. That's kinetic energy, okay? Potential energy, it has it now, right? Extra that I put into it. And then that potential energy becomes kinetic energy when it's moving, and it comes down here. And then it hits my hand. And then that force takes over. It no longer has that kinetic energy. Energy did go somewhere, right? Went into my hand. I felt it. It transferred. It changed form. But it was still there. And now it's gone into this other thing. It went to deform my hand a little bit. Of course, my hand bounces back because, it's not too much of a weight to have broken or damaged anything. So work, energy, potential energy increased, kinetic energy released. Right? Work, energy, work. A little bit complicated, but doable. I hope you understood what I was trying to say in the explanation. And remember, this guy, James Joule, was the guy who wound up making it successful and figuring out the mathematics of it all. So let me give you the mathematics of those things. Okay, I've written down those words and I've talked about them. Now, let me just tell you what they are. Grab another back of an envelope. We have, remember the potential energy, right? The potential energy, that is the stuff that, because I put it in, because I changed its location, for example, right, is the energy that I put into the system so that it can do something, right? And then when it did something, that is fall, right, the object was moving, then that object had kinetic energy. Kinetic energy. Okay. The potential energy of the object was the force on the object multiplied by the distance I held it up here. Does that make sense? So the gravitational potential of that, in this case, right, the force of gravity, which is mass times the gravitational acceleration, multiplied, that's mg, right? Multiplied by the height. So in this case, I would say force times distance. The force times the distance that I moved, okay? That's the potential energy in this case. And then the kinetic energy based on how fast it goes, right? And it changes depending on how fast you're moving. That kinetic energy turns out to be 1/2 m, the mass, again, right, times the velocity squared. Remember, the velocity in this case has both magnitude and direction. But if I just take the magnitude, if I square something, right, you always wind up with, you lose that, again, you're multiplying by itself, right? So you lose the directionality of it. You wind up just having the amount. So it's like the speed squared, the same thing as the velocity squared. So 1/2 mv squared. So the speed, whatever meters per second it is, doesn't matter which direction, square that, then multiply it by the mass, multiply that by half, and that's the amount of kinetic energy. So the amount of speed here that it gains, right, and thus kinetic energy, is basically equal to the amount of potential energy that I added to it earlier, right? From its original position, from here, right, as measured, it has a certain amount of potential energy right now. Then I add that amount of potential, an additional amount of potential energy by moving it up here, force times distance. And then when I let it go, that potential energy is released as kinetic energy. Wow, lots of motion, right? But energy is cool. And we like energy so much, and we like James Joule. We appreciated James Joule so much, right, that the work and energy, the units of it, we've called the joule, okay? And so the name of it is a joule, where 1 joule equals 1 kilogram meter squared per second squared, right? That's 1/2 mv squared, right? Kilogram, and then meters per second times meter per second. That's kilogram meters per second squared, meters squared per second squared, right? But remember that what we were talking about, the potential energy, is force times distance. Oh, so that's got to be the same units, doesn't it? Well, what's force? Force is in newtons, right? Force is kilogram meters per second, mass times acceleration, right? Meters per second squared. Kilograms meters per second squared. That's what that is. Multiply that by distance. Distance is in meters, right? So meters squared up here in energy. If I'm multiplying this by another meter, then I'm squaring it also, right? Newton meter. So a joule is a kilogram meter squared per second squared, but so is 1 Newton meter. So a Newton meter, kilogram meters per second squared, and a joule, they're all the same thing. 1 joule equals 1 Newton meter. And times F. Okay, so to summarize, I want you to watch some of the videos from the Georgia Public Broadcasting physics in motion stuff to understand what's going on here, okay? Let me share my screen really quickly so you can sort of see what I'm talking about. But the study guide for this lecture, and I hope you've already been starting to fill this out up to this point, right, is the idea of understanding what energy is all about, okay? Now, the physics in motion curriculum is great, but we're not covering it all because that's not the same thing that we're doing. For this class is a little bit different from each other physics class, but this material here, if you scroll down, notice the gpb.org/physics in motion, right? If you scroll down and look at this, momentum and energy, okay? You can see that you have segment A, B, and C. They're about conservation momentum, impulse, which is force times time, collisions. And now there's work, kinetic energy, gravitational potential energy, and work energy theorem, okay? So I want you to take a look at segments D, E, and F. Each of them are not very long, but those are what describe and explain what energy is about, energy work in terms of kinetic and gravitational potential and how they connect with one another, work and energy. What is their connection? Okay. And by watching those, you will get another sense, another way of talking about what I was just demonstrating with the water bottle and things like that. All right. So that's what we want to talk about energy. I want you to try to understand and internalize what it means. We'll see many different examples of how energy shows up in the rest of our lives and the rest of how it manifests. Okay, so don't worry about that. Lots of really cool stuff. Enjoy it. Okay, this is your first step into understanding how energy works. And you'll see energy elsewhere. Eventually, you'll see like what the coal and the natural gas and the oil and the gasoline and all that kind of stuff, how that matters and how that works with the energy balance of the world and of the universe and of our bodies for that matter. You know, how does what we eat turn into energy? All those things are really, really cool, and it's worth taking a look at. Okay, so thank you. I really appreciate it. Thank you for being here. We will talk again very soon. And do those study guides. If you have any questions, of course, ask me, ask your recitation instructor, ask your lab instructor. We will have all kinds of fun conversation. Thank you so much. I'll see you at the next lecture, okay? All right, thanks. Bye.